An extremely cosmic high-energy particle has fallen to Earth and its origins are completely unknown. This big beam from outer space is a seismic celestial event and it hit Utah in the United States. Called Amaterasu after the Japanese mythological sun goddess, it sailed into Earth carrying a huge amount of intergalactic energy, which scientists believe is from another galaxy.
Amaterasu is a prominent deity in Japanese mythology and is known as the goddess of the sun. The origins of her worship can be traced back to the ancient religion of Japan, Shinto, which is still practiced today. According to legend, Amaterasu was born from the left eye of the god Izanagi when he purified himself in the river after visiting the underworld. She was considered the most powerful of all the gods and goddesses and was believed to bring light and warmth to the world. In one well-known myth, Amaterasu became upset with her brother Susanoo and retreated into a cave, plunging the world into darkness. The other gods tried to lure her out, but it was not until the goddess of mirth, Ame no Uzume, performed a lively dance outside the cave that Amaterasu emerged, intrigued by the commotion. She saw her reflection in a mirror that Ame no Uzume had brought and was so pleased with her own beauty that she came out of the cave, bringing light back to the world. Amaterasu's importance in Japanese mythology is reflected in her inclusion in the imperial regalia of Japan, which consists of 3 sacred objects: the sword, the mirror, and the jewel. The mirror is said to symbolize Amaterasu and her role in bringing light and clarity to the world. Today, Amaterasu continues to be an important figure in Japanese culture and is often depicted in art and literature. Her legacy lives on in the hearts and minds of the Japanese people, who continue to honor her as one of their most revered deities.
Unlike the low-energy cosmic rays that emanate from the sun and are all around us, invisibly passing through our bodies every second, high-energy cosmic rays are extraordinary. These super powerful particles are millions of times more powerful than any man-made machine, like, for example, the Large Hadron Collider.
Large Hadron Collider, LHC, at CERN, the European Organization for Nuclear Research, has become a focal point of revolutionary scientific discoveries.
Particle accelerator altered the weight of one electron and therefore destroyed our universe and shifted us into the universe that's directly next to it, and therefore things are different in this universe.
This video elucidates 10 compelling reasons why scientists conjecture that CERN has unlocked a portal to an extra dimension, launching us into a new realm of understanding about the cosmos. Number 1. Observation of unexplained phenomena. The Large Hadron Collider, LHC, at CERN is the world's most powerful particle accelerator. At its core, the LHC is a 17-mile ring buried under the France-Switzerland border near Geneva, where subatomic particles zip around at nearly the speed of light. The LHC allows physicists to recreate the conditions that existed a fraction of a second after the Big Bang. During the early operation stages of the LHC, several unexplained phenomena were observed that baffled scientists. For instance, detectors in the LHC started recording an unexpectedly high number of particle collisions at certain energy levels. These anomalous events did not match predictions based on the standard model of particle physics, which has been the cornerstone of our understanding of the subatomic world for the last half-century. Additionally, a series of experiments dubbed as beauty experiments were aimed at measuring the decay of beauty quarks, a type of elementary particle. The results showed discrepancies with the predictions of the standard model, again pointing towards the presence of new physics beyond our current understanding. Anomalies were also observed in the behavior of neutrinos, which are ghostly particles that barely interact with matter. CERN's OPERA, Oscillation Project with Emulsion Tracking Apparatus experiment detected neutrinos seemingly traveling faster than light, contradicting Einstein's theory of relativity. Although later attributed to a technical glitch, such observations sparked widespread debate and excitement about the possibilities they could imply, including the existence of extra dimensions. Moreover, LHC's experiments also produced heavier than expected Higgs Boson particles.
We know what it does, which is it gives mass to everything. So it's fundamentally the thing that gives mass to all the other things in the universe at the most fundamental level. So electrons, for example, and the up and down quarks, they get their mass from their interaction with the Higgs. That's why they're massive. That's another reason we exist. We go right back. We wouldn't exist if there wasn't mass in the universe. And the Higgs is ultimately responsible for that mass. What we want to know is we want to know how that thing behaves. And so you want to study it. So you want to make a lot of them. So you can take a lot of pictures of it and study it a lot and see exactly how it does that. And so that's what we're doing. That's what we're engaged in at the moment. We're making high precision measurements of the way that particle behaves, so we can understand the laws of nature. And that is the laws of nature. How are those particles behaving and what are they doing?
Its latest ray is the second most powerful ever recorded and follows on from a super high energy event 30 years ago named the Oh My God particle. Such high energy waves usually occur after powerful events bigger than the explosion of a star, but scientists are completely baffled by the two largest events, as neither of them can be traced back across the universe to anything, just an area of empty space outside of our galaxy named local void. spaceman. It's very big.
This sparked theories that the excess weight could be the result of interactions with particles or fields in a higher dimension, serving as potential evidence of dimensions beyond our conventional 3 spatial dimensions. Another curious observation pertains to the nature of gravity. Despite being the most familiar force, gravity is the weakest among the fundamental forces of the universe and remains largely unexplained in the realm of particle physics. Some theories suggest that the weakness of gravity can be attributed to its dilution across multiple dimensions, a portion of which could have been accessed by the LHC. While none of these phenomena provide conclusive evidence for the existence of extra dimensions, they have certainly challenged our understanding of fundamental physics. The observations have introduced questions that the standard model cannot answer, thereby pushing the boundaries of science and opening a door towards a possible new dimension. Consequently, scientists believe that these mysteries might just be the gateway to uncovering an entirely new dimension of reality, possibly opened by the behemoth collider at CERN. Number 2. Particle acceleration and extra dimensions. Particle acceleration lies at the heart of the research conducted at CERN. By colliding particles at high energies, scientists aim to unlock the secrets of the universe. In this chapter, we explore how particle acceleration experiments at CERN provide intriguing hints and insights into the existence of extra dimensions. One of the main motivations behind particle acceleration experiments is to probe the fundamental building blocks of matter and their interactions. The high energies achieved at the LHC allow scientists to recreate the extreme conditions that prevailed during the early stages of the universe. It is within these intense collisions that the potential existence of extra dimensions could be revealed. According to certain theoretical frameworks, such as string theory, the universe could possess more than the 3 spatial dimensions we are familiar with. These extra dimensions, if they exist, would be compactified or curled up at scales much smaller than those accessible to current experiments. The LHC's particle collisions, however, could generate enough energy to briefly unfold these dimensions, providing a glimpse into their existence. One intriguing consequence of extra dimensions is the possibility of new particles associated with their existence. These hypothetical particles, often referred to as Kaluza-Klein modes, are predicted to arise from the quantization of the additional spatial dimensions. When particles collide at high energies, the excess energy could be used to generate these elusive particles, leaving behind distinctive signatures in the detectors at CERN. Furthermore, the behavior of known particles could also be affected by the presence of extra dimensions. For instance, in the presence of extra dimensions, particles could move along trajectories that extend into these hidden dimensions. This would lead to missing energy or momentum in the observed collision events, indicating the escape of particles into the extra dimensions. The detection of missing energy or momentum in certain experiments conducted at the LHC has fueled speculation about the existence of extra dimensions. These observations suggest that particles carrying energy or momentum are escaping into unseen dimensions, resulting in an apparent violation of energy and momentum conservation in our 3-dimensional world. In addition to missing energy, the study of particle decays can provide valuable insights into the presence of extra dimensions. The decay processes of particles could exhibit deviations from the predictions of the standard model due to interactions with particles or fields in the extra dimensions. By meticulously analyzing the decay products and their properties, scientists can search for anomalous patterns that could indicate the influence of extra dimensions. While no direct evidence for extra dimensions has been observed at CERN thus far, the high-energy collisions and subsequent measurements provide tantalizing hints that cannot be fully explained by the standard model. These intriguing experimental results have led scientists to believe that the exploration of extra dimensions may be within reach. The quest to understand the true nature of our universe continues, driven by the pursuit of particle acceleration and the potential discovery of a portal to another dimension at CERN. Number 3. Quantum entanglement experiments. Quantum entanglement, a phenomenon in which particles become inseparably linked regardless of the distance between them, has long fascinated scientists and has implications for our understanding of the fabric of space and time. In this chapter, we delve into how quantum entanglement experiments conducted at CERN shed light on the possibility of opening a portal to another dimension. At the heart of quantum entanglement is the concept of non-locality, where the state of one particle is instantaneously connected to the state of another, even if they are light years apart. This peculiar behavior challenges our intuitive understanding of causality and implies that information can be transmitted faster than the speed of light. Scientists at CERN have been conducting experiments to explore the boundaries of quantum entanglement and its potential connection to extra dimensions. One avenue of investigation involves entangling particles and then separating them over large distances. By entangling particles in the lab and then transporting them to different locations, researchers can test the limits of entanglement and investigate whether entangled states can extend into additional dimensions beyond our conventional three spatial dimensions. Such experiments provide a window into the behavior of entangled particles and any potential correlations that could exist across different dimensions. Moreover, quantum entanglement experiments at CERN allow scientists to explore the concept of spooky action at a distance, as famously described by Albert Einstein. If extra dimensions exist, they may serve as a conduit for the seemingly instantaneous interaction between entangled particles. By entangling particles and manipulating their properties, researchers can study whether these entangled states transcend our three-dimensional reality and offer a glimpse into the existence of hidden dimensions. While quantum entanglement experiments at CERN have not directly revealed the existence of a portal to another dimension, they offer valuable insights into the fundamental nature of reality and its potential connection to hidden dimensions. The delicate interplay between quantum entanglement and the exploration of extra dimensions pushes the boundaries of our understanding, paving the way for groundbreaking discoveries that could reshape our conception of the universe. As scientists continue to probe the mysteries of quantum entanglement, they remain hopeful that it may hold the key to unlocking the secrets of an elusive dimension beyond our reach. Number 4. Micro-black holes and their implications. The possibility of micro-black holes, tiny versions of their massive counterparts, has intrigued scientists and sparked discussions about their implications for our understanding of the universe. In this chapter, we delve into how the study of micro-black holes at CERN provides